Okay, today we are going to see about the brief outline about cyber physical power systems challenge and research needs in the current scenario. Hope we all know that the industry revolution has been coming to the point of industry 4.0, starting from the 18th century to 21st century. And initially it was about they had framed regarding to the hydropower and industrial revolutions. Then they transferred to the electricity market, mass production lines, and all the automation lines. Then they shifted to the programmable machines like PLC, SCADA. Everything has been came into the 20th century. That is Industry 3.0. Then now we have evolved to the big data creation and the smart factory creation with using cyber physical systems. Also, we are evolving with the smart grids nowadays. Okay, let me tell you about the definition of a cyber physical systems. Cyber physical system is the integration of the physical process. That is, the physical process may be anything like electrical systems or mechanical systems or any plants, anything, which is with an embedded computations. The computations in the sense we have all the control part and the monitoring, everything, sensors, everything will be integrated in that, along with the network monitoring. Network monitoring can be the internet monitoring for the remote monitoring of the plant system. That is a physical systems. Usually, we will say the cyber physical systems has three C's. That is the communication, computation, and control. Here we can see that we have the set of information, that is the big data. We all know that we have the collection of data will be there. Using that, we can do the computation process with the physical systems. Then there will be a control for the physical system, and there will be communication. The communication will be based on anything like Wi-Fi or LAN. Depends upon the requirement, we can configure that. Then the control and monitoring of the physical systems can be implemented. Okay, you can see the applications. What are the applications by using the cyber physical systems? The smart grid, smart transportation systems, the smart manufacturing systems, robotics, agriculture, and healthcare. These are the major applications of the cyber physical systems. And starting before cyber physical systems, we more learned about the embedded systems, everything, IoT and all. But how it can evolve to the final stage, that is the current stage now. Initially, we have the embedded systems with us that will communicate the cyber world, that is the internet, along with the physical world. That we has been evolved from 1960s to 2000. Then from 2005, they had framed a cyber physical system concept, that is the industrial 4.0 concepts. From that, there will be network-based communication between the physical and the cyber world. There will be a common network between the cyber and the physical world will be there. Then now it has been evolved. That is to cyber physical social systems. That is from 2013, it has been emerging. It's one of the emerging field. In that, there will be a strong network between the cyber world, and that's the physical and the internet, along with the social world. In this, we can say it as a human in loop. This main theme of the industry 4.0 is the human in the loop. That is the controlled response and how the persons, that is operators, or can be used the physical process, so that the social world is need to integrate with the cyber physical system, so that they integrated all the things together and framed it as a cyber physical social systems. And currently we are using the and modeling based on this only. Okay, then you can see some basics of cyber physical systems. That is, as we know already, know that the cyber physical systems is basically a three C's, that is communication, control, and controlling. Then the cyber physical systems, there are certain important things like it should have the human loop concept, then policy decision making, then cyber security and privacy, optimization and control will be there. These are the primary things which cyber physical system should have. From this, the next, optimization and control and cyber security privacy, it has different parts. Like for using optimization and control, we need wireless sensing, adaptive control, high performance computing, and network control and estimation should be there. These are the elements needed for the optimization and control. By coming to the cyber security and privacy, the privacy and protocol should be framed properly. Then network and cloud for that that for data saving the data and the data extraction should be there. Then intrusion detection, then real-time resiliency. So now in the while going to the cyber physical power systems, we need to concentrate more on the network control estimation and real-time resiliency, because for example, if any electrical systems got fault or any problem will be there, it should be attended immediately, or else the resiliency of the grid will be affected and it will lead to the blockout condition. In order to make the grid as a resilient one, the real-time resiliency is maintained based on this cyber attacks. That is, the cyber attack should not be there. Then extreme time scales, risk mitigation, everything should be maintained properly. Or else, if any false data injection is happened in the grid will become the block. Will have then changes in the like per value or a transformer tap changing anything. So it will become a blockout condition. So in order to maintain the grid resilient, the cyber attack should not be there, and all the parameters like risk mitigation, extreme time scales, everything should be maintained properly. Then based on the network control and estimation, the control for uncertainty, like for example, uncertainty of the CPS should be maintained. Like how can I say now? The control algorithm should respond immediately to the uh, problem which occurred in the grid. For example, if turning on any breaker or anything, it should respond immediately. It should not take some delay time or anything. So the response should be prompt. So what are the requirements of CPS at device levels? There are there are four conditions, like connectivity should be proper, data exchange should be proper, then the identifiers, that is identifier of the tag. For example, if you have placing some 100 equipments, the identifier of the equipment should be proper. Then human interaction, already I said the human in loop, so human interaction to the device should be proper. Then what are the requirements for the platform level? This platform level is a integration of device under the system, the physical and the cyber. So in the platform level, we need to ensure the inter-platform interoperability. That is the communication. There should not be any lag in the communication, and also the privacy and the cyber security should be proper. That is, there should not be any false data injection or cyber attack should not be happen in the system. Well, coming to the system level, the system should be autonomy and it should operate in the real time operation. For example, if any control is giving any signal to on or off, it should respond properly within the real time base. It should not have any delay or any unresponsive systems. And also the time management of the system should be proper, and the integration between the all the levels like device level, platform level should be maintained properly. And also the resource optimization, that is what are the equipments are we are using, what are the resources we are using, it should be optimized based on the system level. Okay, basically what are the applications of cyber physical systems in power engineering? As we know that the traditional power systems have the sensors, communications and control infrastructures, as we, like SCADA systems will be there. Well, coming to the power systems as CPS, this is an interrelated physical equipment. Like all the generation, transfer, everything should be interlinked with the cyber SCADA. That is the with network system. That will lead to the smart grids. That so the like human in loop should be there. A proper communication between the physical and cyber layer should be there. So everything should be in the loop. So it's the major application. It's the one of the major advantage of the cyber physical power systems. Everything will be in the closed loop. Okay. As here I show one of the diagram. It's like a centralized power plants will be there. There will be a transmission line. Then the transmission grid is there. From the grid, the power is distributed to the residential load and the commercial load. This is a traditional power system. In this, the flow of information is there, like the energy management and control, automatic meter reading, remote power control, building and monitoring of the data. Everything should be interconnected to the traditional power system. Like also the data will be stored in the cloud for the future use. For example, forecasting of the data will be easy while everything is in the loop. Okay, well, coming to the cyber cyber physical power systems, we need to decentralize the control. Rather, we have the centralized control. In the current scenario, we have the centralized control. The as centralized control is an one control, there is one system, one control. It will have a simple framework like there will be a system will be there C, and the physical system will be C, and the control will be there. We have the input on U and Y will be there. There will be data transfer between that. But what's the problem while going to the centralized control is it will be expensive and need to control all the sensors and actuators from a single system. Rather, um, rather than decentralized, in the centralized we have to control this whole system with a single control. So the sampling data or the measurements error may become. So it's little like an MIMO system, multi-input and multi-output systems will be there. So the efficiency of the control will be reduced. While going to the decentralized control system for the cyber physical power systems, when there is a large system like a whole power system, we can take a whole power systems. In that, the data transfer will be divided into the subsystems. So each subsystem will have an individual control algorithm will be there for controlling the equipments which allocated to that control. So in the decentralized control, the major advantages is it's a local information. For example, if you connect a local controller for one transformer, the control will be especially for that transformer alone. So it will take care of all the problems or solutions which on the control, and also the data which obtained from the decentralized control will be transferred to the main monitoring station, so that they from the centralized monitoring station they can easily segregate the control and actuation of the subsystems. And the main examples of the decentralized controls are transport system, communication networks, power systems, and economic system, manufacturing. So while using the cyber physical systems, decentralized control, not only in the power systems, we can use it for the manufacturing or in the transportation systems. Anything we can use for the any centralized control into decentralized control. Another thing, while going to the decentralized control, the centralized control systems need to be divided into subsystems, and also the parallel processing and the distributed computing algorithms need to be implemented in the decentralized control systems. Okay, as I said, the decentralized control is one or many systems and many controls working in a parallel thing. In this, the classical control will be there, and the lot of data will be stored in the each subsystem. One major advantage is it is easier for communication and computation, but the major disadvantage of this decentralized control system is there will be an cyber attack or a vulnerable data injection to these communication networks, because there will be a lot of communication networks will be in the decentralized control system. Since there are three subsystems are there, C1, C2, and C3. We have U1, Y1, U2, Y2, U3, and Y3, and the whole centralized system is there. So to get data from each system, we need to communicate with each of the subsystem with the network control. The hackers may easily inject the data in this if there is a cyber security error. Okay, what is network control systems? Like network control system is the control loops which can be controlled through the network. It can be an anything like plant and controller will control through an network, like substation, and another substation will be controlled through a network based system, and we can control each other. As I said, there is a distributed controls in the previous slide, C1, C2, and C3. Here it is connected to the communication network. From that, there will be sensors and actuators which are connected to the physical plant. The physical plant may be anything like transformers or power plants or any loads or any whole substation can be anything. It depends on the thing which we had applied. And what's a decentralized network control? Like it's a decentralized network control is an it's part of decentralized control. In this, the data should be exchanged locally with the communication networks, and Also, the reason why we are going for the decentralized network control is perturbations of data exchange through the decentralized control will be good, and also the privacy issues can be avoided while using the network controlled systems, and there would not be any time delays in the control actions taking in the system. Okay, while coming to the communications of power systems, like what are the communications now they are followed, like real-time operation communication, operation communication, and administrative communication. These are the three communication systems they are using in the power system communications. What's the real-time operation communication? Uh, it's a real-time operation data. That is, a real-time data is transfer between the systems. It like, while going to the teleprotection, in this there will be an very short time of 12 to 20 milliseconds. There will be an a data transfer should be there, and a fault disconnection will be in at the time of 100 milliseconds. Then while going to the SCADA systems or EMS, there is energy management systems, there will be a supervised control of the power system on the secondary level, and the data transfer, that is the data will be collected in each 15 seconds. And also using the real-time operation control, we can use the voice communication between the between the systems. Like nowadays they are using the power line communication, right? Based on that also we can use with the real-time operation control. What's the administrative operation communication? The administrative operation communication is mainly for the equipments they are you are fixing the power systems, like um, the asset management of the equipments which are like transformers, transmission lines, what are they using for the asset, then the fault location, the meters, and other informations, and the security system, substation, and camera for the supervision. These are the data which will be collected, and it will be maintained based on by using the local recorders and disturbance recorders in the stations. So the communications which used for the asset management and the equipment managements are called administrative operation communications. What is administrative communication? In the administrative communication, there is a voice communication between the voice and facsimile communication between the two different geographic location offices, like two substation will or two load dispatch centers to load dispatch centers will have the communication between them with using the power line. So it will be in administrative communications. These are the communications they're using in the power systems. Okay, what are the developments involved in the power system controls? Like the mainly the control of the power system is the main nerve for the main nerve, and also the essential things need to be controlled and moderate the power factor, and the power flow and the power demand should be controlled properly. These are the things which they will taken care while controlling the whole power systems. While coming to the IT communication systems, they need to maintain the privacy of the data which they are transferred between the two stations, or to from the station to the equipments, everything. So they need to taken care of that. Also, what are the cybersecurity issues we are facing in the system? Like there will be four sections are there, like decoupling of between operations SCADA and admin IT, then threat and possibilities, SCADA system and SCADA security, information security domains. These are some of the things in the power system control. We are facing the cybersecurity issues in the power system control. Coming to the decoupling between operations SCADA and admin IT. In this, the existing SCADA will be updated using the information from the remote station and all. And also, we need to update the SCADA and EMS system based on the digital threats which will affect the system. For example, it should be protected from the cyber security problem. For example, we need to like if anyone is injecting any false data in this, the firewall should protect the system. It should will protect the system, and it should not affect any other data transfer. Also, and it's mainly between the admin of the IT. Like the admin means there's a centralized control center will be there. They will have the proper firewall, and the SCADA and EMS sensors and actors will be in the plant. So the data transfer between the both should not be interrupted, because if any false data is injected in between the system, the network will become blocked out. So whole power system will be resulted in the blockout condition. So the SCADA and admin IT privacy should be maintained properly. What are the threats and possibilities? So here there is an access points of the SCADA system is there. Um, there are remote locations or SCADA and EMS monitors, everything is there. There will be band communication. There is wireless communication is between the substation to the access points. So the hackers can easily route the band communication and they can uh, inject the false data in this. So by using the false data injection, they can easily change any values like turning on and off of any system or any asset management system. They can remove the asset management in the systems. So they can do whatever they think. Like that only the if any cyber attack is happen in the system. What is SCADA security and systems? In this, the critical information should be protected properly. In the SCADA security, the system will have the cloud data will be there. So the critical information infrastructure protection, that is main thing in the SCADA system security. So we need to protect all the datas properly in the cloud or in the any system which the data is continuously recording. Then what's the information security domains? Like what are the domains which the cyber security problems will occur? Like it's a public supplier maintainer, then power plant, substation, telecommunication, real-time operation, and the corporate IT. There is admin. So the problem can be occurred at any point of any connection point. We cannot define that it can be occurred only at this point. So the 6 domains are there. In any domain, the cyber attack can be happen to affect the power systems. Then privacy and security threats in this. What are the types of attacks happen in the cyber system? It's the denial of services, the DOS attack. In this, the overload is overload a cyber system with multiple requests. So if you take a system, for example, if any user is requesting an thing to on or off, but while there is a DOS attack, for example, if you give one request, it will commit 10 or 20 requests, depends upon the manipulation done by the cyber hacker. We already know that in our PC itself, if any like any virus attacks is there, means if you open a single file, it will keep on opening the multiple files. So same as that only, there will be an multiplication of the request is there. And what is a cyber attack? It is an attack with the decentralized and peer-to-peer systems. As I said previously, there will be subsystems of control will be there. There will be overall whole system will be there. For example, any attack is happened in the decentralized system, it will affect the particular system alone. So in the Sybil attack, they are mainly they are attacking the decentralized control part. For example, if they attack any, for example, there will be a transformer and transmission line, any circuit breaker is there, they can attack any one of the port, maybe the circuit breaker or the transformer. So like that, the attack is decentralized attack. Then it is a black hole or sinkhole attack. It is attack infected with the data traffic, infected in the data traffic. Like the data is data packets are transferred between the two systems. So they are taking the control of the data packets which can be sent to the some system. For example, if C1 will be on subsystem and another system is another main system is there. So if there is any data transfer between them system, they are taking the control of the data transfer and they're making it null or any manipulation will be there. And what is a wormhole attack? The wormhole attack, attacker records the data at a selected location. It's also literally equal to the black hole. So a black hole and wormhole is specially for the particular location. Okay, we'll see the foundations of cyber physical systems. Usually the cyber physical systems will start from the sensor networks and distributed sensor networks. We have like There will be a set of sensors will be there with connected to the system, and there will be a network will be there with the database administrator, and the users can see the value data, and they can manipulate anything, like they can control and operate from the virtual location, like it can be an offshore location or onshore, that is the workstation. So if the sensor networks are distributed, that is we can easily but we can easily fix the distributed control in this. So the main requirement of for the decentralized control is distributed sensor networks. And what is embedded systems? As we know that embedded systems, the possibilities with the physical systems and the cyber. In this, there will be an tightly coupled between the cyber, that is the process and software, and the physical process for the specific task. As we know that there will be human in loop, so there will be human interface will be there, and the software and the electronic hardware required, the control will be implemented in the software, and the sensors and actuators taken care of the of controlling the physical systems. And it comprises like the software, electronic hardware, and sensors whole comprises as the embedded systems. And the system which need to controlled is the physical system, and we can monitor the responses and all other control and response from the main system. Okay. What is the secure network control systems? As we know, the distributed networks will have the distributed sensors, actuators, communication networks, which required for the processing of the control systems. In the secure network control system, there will be a subsystem, like subsystem 1, subsystem 2, subsystem up to n will be there. So each of the subsystem will be secured, and the data transfer will be taken care to the communication network. So the problem they are giving the yellow or all possible at false. So the false which can be like the that any data manipulation or any cyber attack can be happen in the secure network system. So the before implementing itself, they will identify the problems, and they will protect the system based on that. For example, they will keep proper firewalls for that, so other user can't enter into the systems. And also there will be an cyber security protection is there. What is the distinguished features of cyber physical systems? So the CPS is, we know that CPS fully rely on the distributed sensor network with multiple inputs and outputs in the system, and also the human loop should be there, and also real-time response and demand control should be there. And the first thing is the computational needs with adaptive and variable number of inputs are essential for CPS. So the proper computation model should be there for the memo system. Usually it's a multiple input and multiple output system. So the proper computational models with the adaptive and variable with the proper input output should be there. Then second one is the CPS should be distributed and collaborative computation model. So as we said, there will be a parallel communication will be there, and a decentralized control will be there. So it should be taken care. Sorry, the point also same. While coming to the modeling of the CPS, there will be discrete and continuous modeling. It depends on the requirements and the system which we are using. So for example, if the system which needs both continuous and discontinuous model, they is called as hybrid systems. Nowadays they are using co-simulation methods and meta modeling methods for modeling the cyber physical systems, like the real-time computation. The real-time controllers nowadays are taking major role in the cyber physical power systems. Like we know that real-time simulators like Opal RT, RTDS, and Typhoon, they're playing a major role in the real-time computation of the power systems. So in this, the main reason is there won't be any delay in the data communication or control. It will operate in the real time, even though it is in an dedicated real-time system. Real-time control will be there, and there will be an host system is there. So for the monitoring and collection of data from the transformers or circuit breakers, everything should be will be in the real time, and the decision making will be in the real time. So there won't be any delay in controlling the equipments. Well, and the interaction with the physical world, like we can take the sensors or process and control systems and the communication networks which need a proper interaction with the physical world. That is, physical world maybe the any equipment which needs to be controlled, and the interaction between the sensors and actuators from the communication, that is a decentralized control systems to the physical world should be proper. There won't be any delay or any miscommunication should not be there. And also we need to take care of the memory size of the memory size of the program which we are implementing in the processor, and the power of the processor, how much the power it is consumed, and also the speed, how much speed it is responding, what's the speed of the response. Also we will take care all the things together, and the interaction of the physical world is the main thing in the cyber physical power systems. What are safety critical applications? Like we know that there will be a failure or any damage to the environment, it should be immediately informed to the centralized control systems. And also the failure of the equipment should be monitored properly, so that the testing and validation and certification of the systems is important before implementing the final stage. Solely we are using the simulation methods before we are starting with the hardware. So proper testing and validation certification is required before going to the implementation. And some of the critical applications are the healthcare, transportation. Transportation, we need to test the proper output. Like for example, the demand required for the one house is 500 watts, but the control is giving 600 watt or 200 watts. So it should not be there. So proper control should be there. For that only they are framing the test benches for verification and validation of the proposed systems. What are the cross-cutting technologies which can be used for the cyber physical systems? That is abstraction, modularity, and composability, and there will be proper standards and interoperability be there. Then the system should be adaptable and predictable. The control should be predictable. For example, if we have the data in the cloud, there is a big data in the cloud, it should be the algorithm which we are using should predict the proper load forecasting, and the hierarchy of the control should be proper, and the network should be secured, and there won't be any problem in the resiliency of the grid. And also autonomy and human interaction should be maintained properly, and need to take care of the cyber security issues which will be there. So these are the cross-cutting technologies which can be used in the cyber physical power systems. Also another main thing in the cyber physical power system is we need to design a controller or processor which can be reconfigurable, so that if any problem occurs in the system, it will automatically self-heal and reconfigure to the some other control. For example, if any one control point having any communication error, it will automatically transfer from one to another. And main design objectives and challenges while framing the test beds are modularity. In this, being the we have different functional units, so each of the functional units should be abstracted, and it should be interacted properly. And scalability, in the scalability, it can be like for example, if it's starting a system with some 10 equipments, it can be easily increase the equipments to 20. So the scalability of the system should be there without losing the data or any um, miscommunication in the system. And repeatability, in the repeatability of the test bed, the trials, for example, the test cases will be fixed in that, and it will automatically evaluate the test cases, and the results will be generated. For example, if you design an inverter, so if you the inverter can be same inverter can be kept in the test bench, so repeatable test will be taken care for some hours, and even though even overnight also. So the each and every load changes and frequency changes, what are the test cases we had given, it will take care all the data like repeated trials. And reconfigurability, in the reconfigurability, as I said before, if any problem in the one communication port, another communication port will automatically assigned through the algorithm which we have framed. So the test bed which we have designed should be have the capability of reconfiguration. And the interpretability. In this, the components in the test bed should be easily replaceable, and there won't be any problems in the communications or the protocols which we had used. Easily, if any problem occurs in the single component, that should be easily replaceable. It should not make any complex, like again we have to make new algorithm or anything. It's like an plug and plug and play system. Okay, in the test beds we're using for the validation, it will have an physical layer. That is the physical layer here. It may be a hardware or some power system simulators. It will be connected to the communication layer, and there will be information control layer. In this, the monitoring and control will be taken care. For the monitoring control, there will be an EMS, energy management systems, or RT real time control units, or RTDS will be there. In this, what are the problems occurred in, between the information and communication layer will be there, where cyber attacks can be happen. And in order to protect the cyber attacks, there will be defenses like network protocols and firewalls will be protected, will be there to protect the system from cyber attack. So these three comprises of the test benches, like there will be a physical layer, communication layer, and information layer. And in the power system layer, that is on physical layer, it can be any electromagnetic simulator or electromechanical simulator or hardware will be there. In the sensor layer, it is an simulated software sensor, or it can be a hardware sensor. In the communication layer, it can be a software communication or hardware communication emulator, and there will be an application layer. There is a control and monitor layer. So depends on the requirements, we can use it anything like it software or hardware based on the systems and the requirements. Okay, here I shown an example here. They are used RSCAD and RTDS for as a power system layer, and for monitoring layer, they interface with the hardware Ethernet control, and then some PMU is there, and database is for storing the data. This is known as monitoring layer. Then there will be a communication layer. In the communication layer, they use a control center node with distributed control. Then there will be control and application layer. In this, there will be a control center, and a real-time monitoring will be there. So these are some of one of the example taken from the references based on the implementation of cyber physical power systems. And we can use LAN for the communication of the dispatches, like power systems will be there, contingency description, power control systems will be there, and together it is coupled to the power simulator. Then there will be a LAN switch. It is connected to the wide area control software, and the results are saved in the big data. And another, we can use an WAN communication, wireless communication. In the same, here we have the power system simulator, and the controllers are connected to the LAN in the one part, and another will be like an WAN will be there. It is a data lab will be there, and from that the time series results is obtained. So we can use anything like LAN based or WAN based, depends upon the requirements and the needs. Okay. So nowadays we hear about the digital twin or cyber twin for implementing the cyber physical power systems. In the cyber twin or the digital twin, it is a virtual target. For example, we will have the physical target here. Same as the physical target, there will be a virtual plant. So the both will be communicated together using the sensors and data, and from that data we will have some analytics will came out of from the virtual model, and it will be given to the actuator. So both model will have the like it will compare itself, and if any changes occurs in the real system, the digital system will take care of the control, and it will optimize the requirements of that, and it will for example, if you need any reconfiguration of the system, it will be done through the digital virtual plant. Okay, while implementing the digital twin, we need to take care of the 6 points, like create it, in create there will be a procedure for measurement of the physical target, and while going to the communicate, the communication between the physical and digital platforms will be taken care here. And aggregate is a data analytics processing between the real-time data, or it can be taken from the cloud data. And what's analyze in this, the data will be aggregated together, and which can be used for visualization of the collected data from the physical devices. And the insight is also same as the data analyzed from the thing. And the main thing for insight is we need to identify the differences. For example, in the physical system, any problem occurs, it should the digital the virtual power plant, the virtual system which we had designed will show the differences. And act will be an intelligent act. So we have the measurement, communication, and data processing and identification of the data using insight. So we all did this to um, act the intelligent action for the physical target. So in order to maintain the proper control of the physical target, we need to take care of all the things like create, communicate, aggregate, analyze, and insight. If everything's work properly, so that the act, there is intelligent action for the physical target will be fine. Okay, what are the general cyber physical emulators which can be used for power systems or power electronic studies? That is, first one is the cyber physical core simulation. In the cyber physical core simulation, there will be integration of different software engines. Like it can be MATLAB, LabVIEW, or a PSIM, a Typhoon. Anything can be there. There will be data transfer between the two simulator engines. Like we are the communication network. There can be, for example, if plant is modeled in one software, and the control will be in one software, and the monitoring will be in another software. So three should be coupled together, and it will give the response as the real time. And another thing is cyber physical hardware in the loop. In the hardware in the loop method, in this there will be integration of hardware and software is there. And also the plant model. The plant model can be any power system model or power electronics model, which will be designed in the host computer using any modeling or power system or power electronics modeling software, and it will be communicated to the processor, which is outside. There is a real processor. It can be any DSP or FPGA processors outside the host computer, and everything will be integrated with online monitoring and control. And another one is cyber physical rapid control prototype. In this, there will be a real processor and real controller will be there, along with the reconfigurable processors and data acquisition systems for control and monitoring of the physical device. What are the challenges we are facing in the cyber physical power systems? Like this, first one is the technological challenges. The technological challenges, we will face the problems like distributed control, autonomous, reliable of the system, and cybersecurity problems. These are the major problems which can be occurred in the technological challenges. So while coming to the two factors, contributing factors of the challenges are, it's one will be the economic and scientific aspects. In the economic means there won't be any like economic loss should not be there, and also the scientific in the sense we need to maintain the privacy of the system, so that the blockout condition will not arise here. What are education challenges? In the education challenges, in this, it is a multidisciplinary thing while going to the cyber physical power systems. So in our, like it's an integration of computer engineering or civil engineering, electrical engineering, mechanical, everything should be integrated in the right balance, so that the integration should be proper. So while coming to based on that only we can develop the test benches like in the cyber physical laboratories, so that the designer should have the interdisciplinary knowledge for creating the test benches, because it will have physical components, cyber components will be there. The cyber components will be taken of the computer science engineers, and physical, it may be anything like electrical or mechanical system, so it can be taken care of by the electrical or mechanical engineers. So the interdisciplinary knowledge should be there for creating the cyber physical systems. And also the engineers required education training in the multidisciplinary. What are the legal challenges? The legal challenges are like the data safety. The data safety should be maintained properly, and the security of the systems. For example, if you have the electric components in the system, transformers or transmission lines, everything should be secured, and it should not be theft, or it should not be um, have any problems with that. So that legal challenges should also is a major problem in the cyber physical power systems. For that, we need to but testing and certification should be there for the control. For example, if any equipment is going to theft, it should be properly informed to the substation or the main control center. Okay. Then what are the challenges in the lifespan? For example, if we are using sensors and actuators for the control and monitoring of the system, we need to check the lifespan of that, how much time it can run, and whether it need any replacement of battery or any replacement of the component for a particular years, and also cost. If you are going to implement a cyber physical power system, it should be minimal cost, and it should be I should not like the budget should be maintained properly for data acquisition technologies or the construction components which we are using. So cost should be optimal. And what are the trust issues? As we said, we have an potential cyber security, and also the resilience of the system should be maintained. So these are the challenges in the cyber physical power systems. Now, what are the opportunities which we can be using in the power systems, like the autonomy of the system or the health healing properties and the resilience of the system can be made better by using the cyber physical power systems. And also there will be an proper coordination control in the large systems, like for example, the interstate power systems will be there. There will be proper collaboration and coordination will be there. And also uh, that we need to take care of the false data injection in the system, and also the social awareness should be there for supporting the systems. For example, if there will be a human loop in system, so while using that human loop in the system, the workforce, that is the employee, should be skilled, and they have the better knowledge for operating the systems. And what are the security solutions for the sensor networks? What are the solutions we need for maintaining the privacy of the networks? What is the encryption? The data should be encrypted between the two networks so that outsiders cannot access this data. And communication under security, which is that the device and the platform which we are using which should automatically reconfigure based on the problems. For example, if any problem in one data point, the reconfiguration should be there, and it will automatically transfer to the next communication point, so that the hackers or more hackers or malware software which cannot access the communication point. And data aggregation, what's in the data aggregation, while we have the collection of data from any hub or any remote station, so that the data transfer between the data center and to the substation should be secured. So in order that the attackers can't enter into the system and they cannot manipulate the data. And we see before we see the basis of our cyber physical systems and control, distributed control, and centralized control, and what are the problems we are facing in the cyber security problems, and what are the things we need to take in care, and what is a digital twin, everything we saw on that. And in our lab we had developed in 3 test benches, that's cyber physical core simulation, cyber physical hardware in the loop, and cyber physical rapid control prototype. These are the 3 test benches we had created in our lab for evaluate for the case studies of cyber physical power systems. The first one, we designed a rapid control prototype. In this, the real plant there will be real plant and real controller. The main thing of the test bench is we need to analyze the system with ICT capabilities and cyber physical capabilities of the system. In this, we are designed a cyber twin model of a plant, and also there will be a real system, so we both will interact together, and the proper control systems will be there. Okay, the softwares used are Labio and multisim packages. This we have an Poltronics model. This is a real model, and there's a data acquisition and control will be there, and it is connected to the cyber pin. And the Poltronics model is modeled in the multisim packages, and there will be an monitoring and control algorithm. Okay. In our lab, we had developed a back-to-back converter with based on current source converter with multiple outputs. Here, the controller is based on sliding mode control, and there will be an host computer with cyber twin models. Also consist of DAC and a reconfiguration Rio processor, that is a reconfiguration processor from National Instruments, and we also have the cyber layer. From that, there will be a control and monitoring session will be there. So here the physical layer is the converter, cyber layer is internet connection and the monitoring. As we said, there will be a physical layer is there. There will be then photonic converter, and there will be a cyber layer, and there will be a cyber physical integration layer, which has an host computer with the DAC and Rio processors, along with the sliding mode, integral sliding mode controller. These are the, as we know all that, these are conditions for control, and these are PWM signals which we obtain from the controller, and these are the outputs. Here the capability of the back-to-back converters in this is it can deliver equal and different voltage mode in the output. For example, the first output can be some 100 volt, and the second output can be 50 volts. So we can change the magnitude also in this converter. Rather, the other converters will have the same output and same there's the same magnitude will be there. Here we had modified the design, and so that we can obtain different voltage levels also. And this is the CPS monitoring screen. There will be a link will be generated based on the NI server, and all the control signals, the voltage, the current, and source voltage, rectifier voltage, and the DC current, everything will be monitored through the internal monitoring screen. So the physical layer is the physical layer is back-to-back converter, and the cyber physical integration will have the host computer with LabVIEW and multi-sim packages, and there will be cyber layer with the NI server. So whole together we can monitor and control from the remote station. And another thing we framed test bench is cyber physical hardware and loop method. In this also we used LabVIEW and multi-sim based packages, and there will be a DSP processor. Here we used DSP F2812 processor for the control algorithm, and there will be a data acquisition module between the DSP and the software packages for the data transfer and the control of the device. Here we have the DSP processors with sensors and actuators and physical equipment, and there is a target in the target circuit in the multi-sim, and there is a control monitoring solutions like servers, everything will be there, and there is a monitoring station. Here also we had taken an back-to-back converter with three-phase system. Here the cyber integration layer will be DSP processor with data acquisition system. Here the analog input and analog input output, digital input output communication will be there, and the data will be monitored to the cyber layer. And the monitoring screen, as we have the voltage of both the output and the PWM of the inverter, or there is backend inverter, and the current, everything will be monitored from the remote station. Another thing we framed is cyber physical co-simulation based on MATLAB and LabVIEW. Here there will be two simulation engines coupled together for the co-simulation. This one is MATLAB, another one is LabVIEW. Here the simulation model can be done in MATLAB, and the control and the monitoring will be carried place in the LabVIEW based simulation method. In this, there will be a real-time communication between the two softwares using a simulation interface toolkit server. Like we know that the number of models increases, the capability of the co-simulation will be increased. For example, the number of solvers will also increase in this, and number of we have more number of models and we have more number of solvers can be implemented using the co-simulation method. Okay, here we had taken an unified power quality condition system for verification validation of the co-simulation method. Here there will be an power system with source voltage and then load along with the unified power quality conditioner. Here, the unified power quality conditioner is modeled in the MATLAB, and there will be an cyber physical integration layer for with the host computer for control and monitoring, and there will be a network layer for monitoring. And here I showed one of the test case results. In this, there is a source voltage with fault is there, so we can plot the graph of source voltage magnitude. There is a lag in the thing, and there is a compensating voltage. We need to compensate the fault voltage here. This is a compensating current, and this is output current. This is the voltage after compensation. We can get to know that here there is a drop in the voltage after compensation. The voltage become normal, and in the DC link we had used PV and UCAP, that is the ultra capacitor, and this is the magnitude after compensation. Here we can check the magnitude of the source voltage before compensation, and here you can get to know that it is compensated. These are the three test benches we are developed in our laboratory for testing and verification of the cyber physical power systems based on co-simulation, hardware and loop, and cyber physical rapid control prototype. And these are some of the references uh, taken for preparing this course and material. Some of the books and some of the lectures, some of our papers has been taken, and we had shown the content from that. Okay, thank you. Thanks for the session.